So for this session, we're going to talk about some of the properties of matter. And there's going to be a bunch of definitions in this, but hopefully some of this will be review, and for everyone we'll have a good understanding of matter at the end of this. So let's talk about matter and the atomic structure, because matter on its small scale is made up of atoms. And here's the basic structure of an atom. We've got a nucleus in the center, which contains particles called protons and neutrons. And around the nucleus, in different locations, that's where the electrons kind of swarm around the nucleus. So around the nucleus, we have electrons. So let's look at some of these different types of subatomic particles in just a little bit of detail. So electrons, well, they're negatively charged fundamental particles. And we're going to see this term fundamental particles come up. When I talk about a fundamental particle, I'm basically saying something that, as far as we know, is not made up of anything smaller. So electrons, you can't break those into smaller things. These atoms, well, you could break them into their protons, neutrons, electrons, but the electrons, you can't break them into anything smaller. And they're fairly low mass. Protons, well, these are positively charged particles, so they have a positive electrical charge, and they're found in the nucleus. And also living in the nucleus are the neutrons, where we have these neutral particles that are also inside of that nucleus. Those protons and neutrons are made up of yet smaller particles called quarks, and currently we think that these quarks are also fundamental particles, that these quarks aren't made up of anything different. We're not going to talk about quarks too much in this course, so this should be a sufficient kind of view for now. Now, I said that the electrons were negatively charged and the protons were positively charged. Let's talk about electrical charge just for a minute. If I have two positive charges and I put them next to each other, are they going to want to get closer together or further apart if I have two positive charges? Well, if I have two positive charges, they will actually repel each other. If I have two negative charges, they will also try to electrically repel each other. However, if I have a positive charge and a negative charge, those will try to attract each other. The shorthand for this, which we'll be kind of talking about later on as well, for how charged particles will interact, opposite charges will attract each other. So if I have a positive negative or negative positive, they will attract each other. Similar charges will repel. So two positive charges repel each other, two negative charges also repel each other. So yeah, that will kind of come up later on in the course when we talk about these negatively charged electrons, these positively charged protons, and how they interact with each other and with other electrons or other protons. I also mentioned that these electrons have a fairly low mass. And in fact, the protons and neutrons are pretty close to the same mass, and they are about 1,800 times heavier than electrons. They have a lot more mass than these electrons. So this overall structure, if you had an atom the size of the room that you're in, and technically this should probably be like the size of a theater, the nucleus, where the vast majority of the mass is, 99.7% of the mass, would be like a speck of dust in the middle of the room. So imagine in this room a speck of dust in the middle. That's where 99.97% of the mass is, and the electrons are kind of swarming around the outside of that. Most of the atom is actually empty space. Now, these electrons, as they kind of swarm around the nucleus, they can only swarm around the nucleus in specific energy levels. They can't swarm around in any way that they want to. They have to be in specific energy states. And we're not going to worry about this too much right now, but next week when we talk about, later on when we talk about spectroscopy, these electron energy levels are going to become very important, because if an electron absorbs or emits a photon, absorbs or emits a bit of light, well, how much energy they can absorb and how much energy they can emit, that's going to depend on exactly how these electrons are going to make those specific jumps. Again, we'll be talking about that in a lot more detail later on when we talk about spectroscopy, but that is going to have some important consequences. So for these atoms, there's a little bit of terminology that we need. Let's talk about this. So first, atomic number and atomic mass number. So the atomic number is the number of protons inside the nucleus of that atom. And this actually determines what element you have, is just the number of protons. So this determines the element. So for example, if you look on the periodic table, the numbering of each of the elements, that is how many protons they have, the atomic number. So hydrogen is atomic number 1, it has 1 proton. Helium is atomic number 2, it has 2 protons. And going on, like oxygen is 8. So one oxygen atom inside the nucleus, there are 8 protons, because that's the atomic number. The mass number is a little bit different. So the atomic mass number within rounding, if you look this up on the periodic table, you'll get numbers that aren't quite whole numbers. They're either a little above or a little bit below. But approximately, the atomic mass number, when rounded to the nearest whole number, is the number of protons plus the number of neutrons. So it's the number of protons plus neutrons. So, for example, let's say I'm looking at hydrogen 1. Whenever we see this little number in the top left corner of the element, that's telling us the atomic mass number. So hydrogen 1 is atomic number 1, and its mass number is 1. So the number of protons is 1. The number of protons and neutrons together is 1, so it just has 1 proton and no neutrons. Helium-4 is atomic number 2, atomic mass number 4. So if the atomic number is 2, it has 2 protons. If the mass number is 4, then the number of protons and neutrons together is 4, but we've already said it's got 2 protons, so it must also have 2 neutrons. Similarly, carbon-12, that's atomic number 6, and the atomic mass number is 12. It would have 6 protons and 6 neutrons to make up that atomic mass number 12. I do not expect students to memorize the periodic table and know exactly which atomic number each of the elements are. By the end of the course, we're probably going to know that hydrogen is 1 and helium is 2, but after that, I will give you that information if it's needed for the question. One last part about this is, if we have a neutral atom, let's talk about a neutral atom. It has no overall charge. No overall charge. So the overall charge has to be 0 in that case, which means we have to have the same number of positive charges, protons, as we have negative charges, electrons. The amounts of charge that they have are the same, but protons are positive, electrons are negative. So if I have the same number of protons and electrons, that atom will be neutral. So for example, helium, if it has 2 protons and it's electrically neutral, then it would have 2 electrons as well. So let's try an example of this. Let's say the most common form of iron has 26 protons and 30 neutrons in its nucleus. State its atomic number, atomic mass number, and the number of electrons if it is electrically neutral. So pause the video here and take a stab at this one. Okay, so let's look at this in a bit of detail. We've got 26 protons and 30 neutrons. The atomic number is just the number of protons. So the atomic number is just 26. It has 26 protons in it. The atomic mass number is the number of protons and neutrons together. So if we have 26 protons and 30 neutrons, well, the atomic mass number is the sum of those two. That would be 56. If it's electrically neutral, we said there have to be the same number of protons as electrons. So let me actually add that in here. So same number of protons and electrons. So in this case, the iron has 26 protons, which means it has to have 26 electrons if it is electrically neutral. Okay, so some more terminology. We've got the terminology for an isotope. So an isotope, two atoms are isotopes of each other if they have the same number of protons but different numbers of neutrons. So two atoms are isotopes if they have the same number of protons but a different number of neutrons. Basically, this means that they would have the same atomic number, they'd be the same kind of element, but they'd have different atomic masses. So for example, hydrogen-1 has 1 proton, 0 neutrons. Hydrogen-2, which is sometimes called deuterium, is 1 proton and 1 neutron. It's still hydrogen. It still has the same atomic number, but a different number of neutrons. Hydrogen-3, which is sometimes referred to as tritium, has 1 proton and 2 neutrons. So its atomic number is 3 overall. And we're going to see that different isotopes can have different properties. For example, carbon-12, let me talk about this one just for a moment. Carbon-12 has 6 protons and 6 neutrons. Carbon is atomic number 6, so it has 6 protons, and to get the 12 atomic mass overall, we need 6 neutrons. Carbon-14, well, it's still carbon, so it still has 6 protons. It's the same atomic number. And again, I do not expect students to memorize these atomic numbers. They will be given to you. It has 6 protons, but think if its atomic mass, if the mass number is 14, and it has 6 protons, how many neutrons would that have to have? Well, we know that atomic mass number is the number of protons plus neutrons, so together we have to have 14 of those. We've got 6 protons, which means we must have 8 neutrons. And carbon-14 is actually radioactive. It's the form of carbon that's used in carbon dating. Whereas carbon-12, that makes up the majority of the carbon that is around in your body, in the air, things like that. Okay. So let me clear that up just for a quick second. Some other terminology. When I have a molecule is a set of 2 or more atoms held together by chemical bonds. So a group of 2 or more atoms held together by chemical bonds. There are some that should hopefully come to mind, say H2O, water, one oxygen atom connected to two hydrogen atoms. Or CO2, carbon dioxide, one carbon atom connected to two oxygen atoms. And those are held together by chemical bonds. Typically, if you take these chemicals and you keep on raising and raising their temperature, eventually you'll get to the point where those chemical bonds will break and it will disassociate back into their constituent elements, their constituent atoms. But again, in normal kind of everyday circumstances, chemicals are all over the place. They can involve, in some cases, we can have molecules that can involve hundreds or even thousands of individual atoms. Things like DNA strands come to mind. But just in general, molecules are two or more atoms connected by these chemical bonds. So let's try another example. Consider the following three atoms. Atom 1 has 7 protons and 8 neutrons. Atom 2 has 8 protons and 7 neutrons. Atom 3 has 8 protons and 8 neutrons. Which two are isotopes of the same element? So pause the video and give this one a try. Okay, so when we talk about these isotopes, two atoms are isotopes if they have the same number of protons but different numbers of neutrons. So atom 2 and atom 3 both have 8 protons, but different numbers of neutrons. So, for example, the 8 protons and 7 neutrons would be, 8 protons is oxygen, but this one would have an atomic mass of 15, and atom 3 would have an atomic mass of 16, which is actually the kind of more usual form of oxygen. Little bit of final terminology, at least for now. We have an ion. It's an atom that has gained or lost electrons. Now, in our specific case, when dealing with things in astronomy, most of the time, especially when we're looking at things like stars and high energy systems, usually it's going to be the atom has lost some electrons. There's so much energy in there that some of those electrons have been ripped away. So most of the time, when I talk about this atom has been ionized, the default assumption is going to be that we have removed electrons from it. Now, we remember that electrons are negatively charged. So if I add on electrons, well, the overall atom will gain more negative charge. If I remove electrons, I keep the same number of positively charged protons, but I'm removing some of those negatively charged electrons, then we're going to have an excess of positively charged particles, which means that we're going to have an excess of positive charge. And this last little question here, what do you call a hydrogen atom that has lost one electron? Well, remember, for hydrogen, we have one proton and one electron going around the outside of it. So for hydrogen, if I ionize that hydrogen and remove that one electron that it does have, we're just going to be left off with that proton. So let's look at an example. Oxygen has an atomic number of 8. How many times must an oxygen atom be ionized? Again, we're assuming we're removing electrons. How many times must an oxygen atom be ionized to create an O+5 ion? And how many electrons would be left in there? So pause it and have a go at this. So for this oxygen atom, we said it's atomic number 8. So when neutral, we should have the same number of protons as electrons. So it should start out with 8 electrons. If I want to get a +5 charge overall, I have to remove 5 of those electrons. I have to get rid of 5 of those negative charges. So it's missing 5 electrons because it's 5 times ionized. If it started with 8 electrons, it would only have 3 electrons left at the end of this transition. And again, for this course, we're typically going to be assuming if the thing is being ionized, if the atom is being ionized, we're going to assume that it's electrons that are being lost in this case. So again, there's a bit of terminology in there, but again, if there's parts that are open questions about this, please use the discussion board to talk about those kind of questions, because we're going to be using this terminology throughout the remainder of the course. So the last kind of set of topics that I want to talk about for this session are a little bit on how light and matter interact. So let me make a new little section here, light and matter interacting. So matter can emit light, it can absorb light, it can transmit light, and it can reflect or scatter light. So let's talk about each of these examples. Pause the video right now and see if you can think of an example of matter emitting light, so giving off its own light, matter absorbing light, so it kind of captures that light and is now, that light has been absorbed by that material, transmitting light, so light passes right through it, and an example of light being reflected or scattered by matter. So pause it and take a minute to try to identify those before we talk about them. Okay, so let's go through this. Emitting light, so it's giving off light. So it's giving off its own light. What are some examples of this? Well, what about a light bulb? If I have a dark room and I turn on a light bulb, well, that is giving off its own light. It's not reflecting or getting its light from some other source. It's emitting its own light. Your computer or phone screen gives off its own light. If you have a fire will give off its own light. A flame will give off its own light. The sun gives off its own light. Does the moon give off its own light? And let's talk about visible light specifically. No, we only see the part of the moon that is being illuminated by the sun. So the moon does not give off its own visible light. Okay. What about absorbing light? So again, emitting light, that was things like light bulbs, fire, the sun, stars in general give off their own light. What about absorbing light? Well, let's say you have a dark colored car outside on a sunny day. You've gone to campus or something, or you've gone to your workplace, and you have a dark colored car outside all day, and let's say it's summer. What is the interior of your car going to be like by the end of that? Well, it's probably going to be very, very hot inside, because dark colors are very good at absorbing light. So dark colored objects absorb light. Even when you just go outside on a sunny day and the sun hits you and you're feeling warm, I know I'm kind of pasty pale, but when you're even that, it absorbs enough light that you feel warm because of the sun's light. And your body is, you are absorbing that light. It gets warmer from that. What about transmitting light, where light actually passes through the material? Well, the easiest example of that is a window. So light passes through. And we can go with a window for this. Or if you have like saran wrap or something like that, there are different kinds of material, like clear materials, transparent materials, they allow light to actually pass through them. What about reflecting or scattering? Well, probably one of the first ones that came to mind is a mirror. Light can reflect off of a mirror or off of some kind of shiny surface. So, shiny surfaces. But there's one that I want to kind of emphasize a little bit more. When you look at pretty much anything, let's say I'm looking at, let's go with this book, the cover of this book. Okay? It's got an orange spine to it. White light is coming in and hitting this thing, and it's the orange light that is being reflected off of this object. It's being scattered off of this object. A point that is really helpful for identifying what particular colors you see is this. You can only see light that is entering your eye. So let me make a quick note of that. You can only see light that enters your eye. So there's a overhead light here. If I have just a white piece of paper, well, that light comes in, hits the white piece of paper, and all of those colors, all of the colors that make up white light are reflecting off of it, going towards that camera, and kind of changing the gamma on my, how bright the background of my camera is. It kind of seems to auto-adjust. That light comes in, hits the paper, all of those colors reflect and go towards the camera, and you see that paper as being white. Whereas if I have, looking for a quick object to use as a reference, let's say this folder, right, this blue folder, we've got white light coming in, again, a mixture of all different colors. So red light, green light, blue light, all of that light comes in, but we see this object as being blue. What's happening is the blue light is scattering off of this object and going towards the camera, and you see this object as being blue. The red light and the green light is actually being absorbed by this object. And that's another point that I really want to emphasize. For these light matter interactions, different wavelengths can interact with matter in different ways. So let me write that down. So different wavelengths interact with object in different ways. We can also talk about light being transparent or opaque to matter. Transparent light can move through. Opaque, it blocks that light. We're not going to worry about that one as much. Again, what I want to reemphasize is this one. We can only see light or colors that enter our eyes. So let's say that there is a green leaf. You're looking at a tree, it's being illuminated by the sun, and you see this green leaf. Well, white light from the sun's light is white. The sun's light is white. If that white light comes in, again, it has all the different colors. It's got red light, it's got green light, it's got blue light, it's got everything in it. That white light hits a green leaf. We see that leaf as being green because the green light is reflecting off of the leaf and going into our eyes. The blue light and the red light, that's actually being absorbed by the leaf. It's reflecting one color and absorbing a different color. So again, depending on what type of material you have, the pigments of color in that material, what that material is made out of, different wavelengths of light can interact with objects in different ways. Let's do a quick example of, let's say, me and my shirt. I'm wearing a green shirt. It's kind of dark on the screen, but how is light interacting with me? Well, I'm actually emitting infrared light. I am warm-blooded, and in the session when we talked about light, we talked about how warm objects give off infrared light. So I am actually emitting my own infrared light. When light hits my green shirt, again, the blues and the reds get absorbed and the green light gets reflected. So you see my shirt as being green. So again, I've got some kinds of light being absorbed, some kinds of light being scattered. hopefully there's not any X-rays going through the room right now, but let's say X-rays hit my hand. Well, the soft tissue, X-rays will pass right through that soft tissue. My skin is transparent to X-ray light. Again, the point that I want to make here is that these different wavelengths of light and how they interact with matter, different wavelengths of light can interact with matter in different ways depending on what specific wavelength of light you're looking at. Again, you can design different materials, and there are different materials that just exist in nature that will interact with light in all of these different ways. So let's look at some quick examples of how matter can interact with light. For each of these, I recommend pausing the video and trying to identify how is light interacting with the matter in this picture. Assume that we actually saw this painting for real. On your screen, you know that, oh, my screen's producing the light and it's entering my eye. Imagine you're actually looking at this painting and looking in the real physical situation that we're trying to identify. So we're going to go through each of these. Again, I recommend pausing it, trying it yourself, and then we'll talk about these. So let's try this one. How is light interacting with this picture? So we have this painting. We can see lots of oranges and yellows and reds. So if this is being illuminated by just ordinary white lights, all those different colors of light are coming in. The reds and the yellows are being scattered and going into your eye, so you see those colors. Everything else, the more of the greens and especially the blues, those are being absorbed by the painting. So you've got some light being absorbed, some of the light being reflected and scattered. What about this one? Let's say we had a stained glass window. Let's say you're inside of the building and sunlight is outside of the building. And we wanted to know, let's look at one of these blue panels. How is light interacting with this picture? Well, if I'm looking at one of the blue panels, that blue light is making it's white light outside, so the mixture of all the different colors outside, that blue light seems to be able to make it through the panel and reach my eye. So this panel is transparent to blue light, at least these blue panels. Whereas all of the red light and the green light that hits these panels is being absorbed. For the red panels, it would be the opposite. The red light is able to transmit through the window and make it to my eye. Again, we can only see colors that actually enter our eye. And everything else, the greens and the blues, that would be absorbed by these panels. Let's take one last one. How is light interacting with matter in this picture? Well, these neon lights, they are running an electrical current through some gases, and that excites them and causes them to actually give off their own light. Okay, so these signs are actually emitting their own light. There's also some glass panes in here, and the light must be able to transmit through those glass panes or through the glass tubing of the neon lights in order to actually reach our eyes. So again, there's lots of different ways that light can interact with matter, and we're going to be going into more detail in how light interacts with matter and how matter can produce light in a variety of different ways. And we're going to be able to use those properties to be able to say, if I see the spectrum of light from a distant object, what are the properties of the source? How is that light produced? Is there any information encoded in that light that we can kind of interpret to figure out how that light was produced? So we're going to be looking at that in future sessions.